Welcome to the deep dive.
Hey there.
Today we're diving into object relational mappers, ORMs,
Right.
and specifically how a pretty novel graph-based approach might just bring some much-needed order to processing data when you're using them.
Yeah. Sorting out the dependencies.
Exactly. So we've sifted through the research, some general articles, and this one specific scientific paper on the method. We're aiming to give you the core insights fast.
Get you up to speed.
Okay, so first off, what are ORMs really?
The bridge, basically.
Yeah, think of them like translators
Yeah.
or maybe matchmakers between your code, like your Python or Java code,
Mm-hmm. Object-oriented stuff.
your relational database, the tables and rows.
So instead of writing SQL all the time.
Right. You interact using your programming language's objects. A table becomes a class. A row becomes an object instance. It handles all the create, read, update, delete stuff.
Yeah, the CRUD operations. It abstracts away the raw SQL.
So why bother? Why use them?
Well, the big word is productivity, usually. You write less boilerplate SQL
Mm-hmm.
and can focus more on the actual business logic of your application.
And that generally leads to cleaner code, right? Easier to maintain.
Generally, yeah.
Yeah.
Less duplication. And flexibility is another big plus. Many ORMs work with different databases.
Oh, right. So you could potentially switch from, say, PostgreSQL to MySQL without a total rewrite.
Potentially, yes.
Yeah.
Within limits. But it definitely helps.
Yeah.
Plus security. They often handle things like preventing SQL injection attacks for you.
Which is huge. Okay, but it can't all be perfect. What are the, let's say, quirks?
Well, performance can be a thing. For really complex, super-optimized queries, handwritten SQL might still beat the ORM's generated query.
Okay.
And there's a learning curve for the ORM itself, its API. And sometimes, well, the abstraction isn't perfect.
Ah, the abstraction leakage idea. You still kind of need to know what SQL's doing underneath.
Sometimes, yeah.
Mm-hmm.
Especially for debugging tricky performance issues. But still, tools like School Alchemy, Hibernate, Entity Framework,
Active Record in Ruby.
yep, they're everywhere. Especially in web development, really speeds up building applications.
Okay, so that's the ORM landscape. Now let's get into the specific problem this deep dive focuses on. Managing complex data. Dependencies.
Right, the ordering problem.
Yeah, like imagine you're loading a bunch of data. You've got artists and you've got albums. The ORM needs to know the artist must exist in the database before you can add an album linked to it.
Because of foreign key constraints. The database enforces that.
Exactly. And flipping that, if you're exporting data, maybe you want the biggest piece first, the one that pulls everything together.
And doing this ordering manually is, well, it's often a headache. Error-prone, not always consistent.
So this is why the graph idea comes in. Tell us about that.
It's actually quite elegant. You model your data entities like artist, album, genre as nodes or vertices in a graph.
Okay, points in a network.
Exactly. And the relationships, the dependencies, become directed edges, arrows. So if an album depends on an artist, you draw an arrow from artist to album.
Gotcha, like a dependency flowchart.
Precisely. And this forms what's called a directed acyclic graph, a DAGAG. Acyclic is key. It means no circular dependencies. Artist depends on genre, genre depends on artist.
Yeah.
That can't happen.
Right, that would be impossible to order. So having this DAGA structure is the foundation.
It is. It maps out the actual dependencies in your data model.
So how does this help prioritize? There are some specific metrics involved, right?
Yeah, two key ones. First is vertex weight. It's basically an abstract measure of how big a single instance of an entity is. Think bytes.
Okay, like adding up the size of its fields, an integer is 4 bytes, a UUID is 16, that kind of thing.
Sort of, yeah. It's an approximation of the data footprint for one row, including foreign keys. But the really interesting one is movement weight.
Movement weight, what's that?
It's recursive. It's not just the entity's own size. It's the entity's vertex weight plus the sum of the weights, both vertex and movement weights, of everything that depends on it, directly or indirectly.
Whoa, okay. So it measures the total data impact downstream, the weight of the entity plus all its dependents combined.
Exactly. It's the cumulative weight of the whole subgraph rooted at that entity.
Yeah.
You calculate it backwards through the DAG from the leaves up.
Okay, that sounds powerful. How do you actually use these weights then for processing?
Right. This is where the smart queuing comes in. For data ingestion, loading data in.
Like from CSV files or something?
Yeah. You use a min-heap priority queue. Entities with a lower movement weight get processed first.
Lower weight first for loading. Why?
Because lower movement weight usually means fewer downstream dependencies. These are often your foundational types, like maybe country or gender before artist or user.
Mm-hmm.
Loading them first naturally satisfies the foreign key constraints as you go deeper.
Oh, okay. You build from the ground up, dependency-wise. Makes sense.
hmm And then for data egress, like exporting data or serving it via an API,
You flip it.
you flip it. Use a max heap priority queue. Prioritize entities with a higher movement weight.
Why hire first for exporting?
Because higher movement weight typically means it's a more composite entity. It aggregates data from many dependents. Think release pulling in artist, tracks, labels. Fetching these heavy items first often gives you the richer, more complete data structure that an API consumer usually wants.
Gotcha. So you get the main course before the side dishes, essentially.
Kind of, yeah. It aligns retrieval with common usage patterns for complex data.
So the benefits seem pretty clear. Deterministic ordering.
Yep, no more guesswork.
Automated dependency handling.
Adapts if your schema changes too, you just recalculate the weights.
And potentially better performance by avoiding contention during bulk inserts or aligning reads better.
Conceptually, yes. Though real-world performance always has other factors.
Right, limitations. These weights are abstract, not exact byte counts or database performance predictors on their own.
Correct. And it relies heavily on standard ORM annotations, like GPA annotations. If you have really custom mappings, it might need extra work.
And many-to-many relationships. With join tables.
Those need handling too, often treating the join table entry as its own step in the process. It's solvable, but something to consider.
Okay, great. So let's recap. We've looked at ORMs, that crucial bridge between code and databases. And we dove into this graph-based method using vertex and movement weights to systematically and automatically order entity processing.
Bringing structure to dependency management for both loading and extracting data.
Right. It turns a potentially chaotic process into something much more ordered and efficient.
A really clever application of graph theory, I think.
Okay. Okay, so for our final provocative thought, considering how this structured thinking, using concepts like movement weight to understand downstream impact, helps manage data dependencies, where else could that kind of thinking apply? How might thinking about the total ripple effect of components help optimize other complex systems, maybe in your own work or even everyday life, way beyond just databases?
Interesting question. Thinking about cumulative impact. Yeah, lots to chew on there.
Something for you to ponder. That's all for this deep dive.
Thanks for joining us.